Good evening, Sloohers. Paul Cox here with a very special edition of our Practical Astronomy series on Sunday evenings. Well, it's Sunday evening where I am anyway. So, anyway, tonight, why is this special? Well, we've got two fabulous and surprising objects to look at tonight. First of all, we've got the NearEarth asteroid 2018 RC. Now, this little space rock was only discovered on the 3rd of September, so only 6 days ago, and it made its closest approach to Earth about 10 hours ago, and it was halfway between the Earth and the Moon when it made its pass. Now, hopefully you were watching live missions earlier on tonight because you would have caught those special missions that we set up at the beginning of the night. I was hoping somebody's going to share them on the homepage. So if you did snap any, missions, any images from those missions, then please share them to the observation log. And the other object that we're going to be looking at tonight, it's a very special day for this one as well, is Comet 21P Giacobini-Zinner, and this one is at perihelion. In the morning, that's about 8.7 hours away. So perihelion is when the comet is closest to the sun. And in fact, very shortly after, it's going to be closest to Earth. That's around about 16 hours away. But why is perihelion special for a comet? Well, we're going to be talking all about that later on, but basically it means that the sun's heating it up, slamming it with loads of radiation, so that's when a comet gets most active. But anyway, if you are new to Slough and you're just kind of browsing the website at the moment, you need to be going into Livecasts on the left-hand side menu and up to the Space Situation Room. And that's where you'll be able to follow along with what I'm talking about. I'm sharing my screen and stuff like that. So there we go with the old infinity screen. And of course, don't forget, you can click on any of the tabs below and you can see any of the live feeds. So you can be snapping. Let's go over to the Canary 1/2 meter. Oh, look at that. That's pretty. That's going to be a nebula, isn't it? Can't quite recognize which nebula that is. What have we got in the Canary wide field? So, and don't forget, you can snap images. Oh, look at that beautiful globular cluster. So if you are a visitor to the website, you can go to all of these tabs and see the live missions. And you can click the snap button and that will save your very own image of whatever it is we're seeing on the screen. But anyway, you can also go back to it for a second. You can also go back to the live video as well. Anyway, listen, where are we going to go? If you want to ask me any questions about the show tonight, then hop over to the community discussions and the Practical Astronomy thread here, and you can ask me some questions in here and we'll go over those a bit later. Already got quite a few in there already and some nice images to share actually as well. We're going to be talking about a comet's AntiTail, because who knows, we might see one with 21P, and I'll tell you exactly when we can expect and why we can expect to see that. So that's going to be quite good, and the timing is pretty good as well because it's going to be around new moon. But what else are we going to look at? Well, we're going to take a quick look back at some of the great comets that we've seen through Slooh's telescopes over the last decade. We're looking ahead to the special Comet 21P missions that we scheduled for tonight and tomorrow night. Now, there's a really, really spectacular visual coming together of the comet and what's called an open star cluster. So that's what we're going to look at a little bit later. But that's what we've, the missions start in about 3 hours' time because the comet is still rising. We'll take a look at that as well. We are not going to take a look to see how easy it is to set up a comet coordinate mission because we sent out a little tweet. Don't know if you saw that during the week with it took a lot of doing, getting it down to 2 minutes and 20 seconds, which is Twitter's video limit. So I show you there how to get the coordinates from the JPL website and actually schedule that mission in 2 minutes and 20 seconds. In fact, I think it's just under. Anyway, we're also going to take a look at creating a comet time-lapse. Now, we've covered this in different shows, but this is really about seeing Comet 21P in a slightly different light tonight. So that's why we're going to do that. I'm going to show you some different software that we're going to do that. And then, of course, we will take a look at some of your questions and answers and all that kind of stuff a little bit later on. So where should we start? Well, I think let's start at the beginning as, who was it? It wasn't Mary Poppins, was it? It was Sound of Music, wasn't it? Let's start at the beginning. Anyway, look at this. Let's take a look to see what has been happening. And thank you very much, Babak. You have not disappointed me. I can see this is, so Babak is a Slooh crew member, and he's been giving us some great information over in the discussion boards. And Babak has captured this image. This was from the first mission tonight using the Canary 2 telescope. That one is a 17-inch telescope. It's a pretty big darn telescope, frankly. You need to have deep pockets if you want one. But you're certainly going to get my like for that. Now, I wonder if you viewers can spot the asteroid. Well, this asteroid is really, really close to us. And if an object's really, really close to us, it means it's moving fast. So here we can see all of the background stars. We can see it's quite a noisy image. That's because it was the first image of the night, so we were still under twilight skies. But because the object's moving fast, it's not going to be a pinpoint of light. It's going to be a line because it was moving during the 50-second exposure using the CCD camera. And I can see it. It's not one of these long lines. Those are defects on the CCD. But over here, just on the left where I'm pointing, hopefully you can see that little line. And that is the NearEarth asteroid 2018 RC. Now, this thing is thought to be between 30 and 70 meters in diameter. And as I say, it was only discovered, on the 3rd, I believe it was. And in fact, I'm going to, let's just, while we're on this, I'm going to just share something with you, because somebody did ask me the other day, how do you know when these near-Earth asteroids are making a close approach? Well, there's a website here that I'm going to pull up on my screen, and it's it's one of the JPL websites. So let me just make sure that you can see this. There it is, and it's called the Center for Near-Earth Near-Earth Object Studies. Now, a near-Earth object comprises of asteroids and comets. So you can have a near-Earth asteroid within that, and you can have comets within it. But what they do here is they list the upcoming close approaches of any asteroids. And what we can see here is 2018. So they're listed in chronological order. And what you can see here is the date and time of closest approach. So that was earlier today because these times in UTC. And don't forget, UTC is what Slough uses in our scheduling system. And, when you're starting out in astronomy, I would really recommend, if there's one thing you do take the time to learn, is just learn your own local time zone in relation to UTC. So if you're on the East Coast of the United States, you're currently 4 hours behind UTC. Here in the UK, at the moment, we're on British summertime, so we're 1 hour ahead of UTC. Places in Europe are ahead of UTC. So once you get that, it just makes everything a lot easier. And the reason why astronomers use that is because they want to coordinate their observations with other astronomers around the world. And if you can imagine, if they did that, everybody would have to do the time conversions of those observations. Way too easy to make a mistake if you did that. So everybody uses this standardized time zone. So you'll see it on this website, you'll see it on another website I'm going to show you a little bit later, where we can take a look for astronomical phenomena. And here you can see It's showing us the nominal close distance. So this is showing us in lunar distances. So 0.58 lunar distances or 0.0015 astronomical units. So a lunar distance is just the mean distance between the Earth and the Moon. So you can see it's just over halfway between the Earth and the Moon. Astronomical units, that's the mean distance. 1 astronomical unit is the mean distance between the Earth and the Sun. And by the way, I don't know if you know whether to do this. In fact, we'll go to a slightly more accurate reading for that. Actually, here we see the minimums over here. We can see the relative velocity, that's relative to Earth, us here on Earth. We can see the absolute magnitude, it's obviously a lot brighter in the sky. And then here we can see that size estimate. Now that has been changing all week as more and more observations come in. We get the size estimate for one of these near-Earth asteroids based on its apparent brightness. And we can also work out how far away it is because we've calculated its orbit. We take a kind of average albedo. Albedo is an object's reflectiveness. So most asteroids are kind of around the albedo of coal. They're very, very dark objects. But because we can take that as a kind of average, if we know its brightness, if we know its distance, then we can calculate a rough size. And that's why we tend to get these enormous size ranges, these estimates. But when an object like 2018 RC comes this close to Earth, then it falls within the range of radio telescopes. And when they're within the range of radio telescopes, we can actually almost scan the asteroid, and we can actually build a 3D model. So we may, this might be a bit too small to be able to see its absolute shape, but we'll certainly get a far, far better determination of how big this object is through the radar observations that have been going on over the last couple of days. But if you wanted to know a little bit more about this object, you can click on this, and then this opens up another part of the JPL website. So here we can see we're in the JPL small body database browser, and it tells us a whole stack of information here about the object. We can see an orbit diagram and stuff like that for it. In fact, let's just take a quick look at that, see if that comes up. So sometimes it's used to need Java. Not sure if it does anymore. It's not coming up that quickly. So I think we'll hide that bit. Oh, there it is. Just took a little bit of time to come up. So there we can see why it's such a closer approach to Earth, because Earth is actually hidden under its own orbit there. And you can see this crosses Earth's orbit quite a few times. You can also see there they've marked on the inclination of its orbit by those little horizontal lines. So there it is, making its incredibly close approach to Earth just a few hours ago. Anyway, let's take a look. I really wanted to show you this, the close approach data. So you can click on this, and this is where we start getting loads more information about its close approach. You can see here the columns, you can see here minimum distance in astronomical unit, relative velocity, and you can see here that it's computed, even though it was discovered only 6 days ago. All of the submissions that Slooh members have made and other observatories have made of this object are submitted to the Minor Planet Center, which creates what's called a set of orbital elements. Orbital elements allow us, it gives us the property basically of an object's orbit in the solar system. And if we've got that, we can then calculate where it is at any one time and date. So what this has actually done is they've gone back, even though it was discovered, the object's obviously been around for just about ever, 4.5 billion years. So they have computed that it has made, these close approaches before, all the way back to 1900. But let's just scroll down a bit, and we'll get to this particular pass here. And here you can see, in fact, that's its closest approach to the moon. Here on the 9th, 1209 in UTC. That's the object that it was close to. And this is the column, which is in astronomical units. So this gives us a really, really accurate estimate of that. And I don't know if you knew this, but if you just go to Google, in Google, you can type in that number. In fact, I'm having to do it in the, because I'm not actually, let me just load Google so you can actually see that. I've got some fingers that can type tonight. So there you go. So all you would do is paste that in there and say AU and say 2 miles or kilometers or whatever else you wanted. And there you go. It tells you. So 139,000 miles. That is how close NearEarth asteroid 2018 RC got to Earth just 12 hours ago, 10 hours ago. So it's a really cool little thing to do. So so you can just go here to the JPL Center for Near-Earth Object Studies and Close Approaches. If you just do a search actually for Near-Earth Object Close Approaches, you'll get to this page, and then you can see what else have we got coming up this week. And you can see, look at these other distances down here for the other objects that are coming up over the next couple of weeks, over the next 10 days or so. And you can see there 11 lunar distances, 4 lunar distances, 2 lunar distances. So you can see why this particular near-Earth asteroid 2018 RC is kind of so special, because it's a sizable rock, 28 to 63 meters. 28, that's at the kind of range that the Chelyabinsk meteoroid was that impacted the skies in Russia. It was about 20, 30 meters, wasn't it, I think? So 3 times that, you start getting close to 100 meters in diameter, and then you're looking at objects that can make it through the atmosphere without totally burning up. So in other words, could impact. But as we saw from Chelyabinsk, even that atmospheric detonation, when the thing just vaporizes and explodes, it was the sound shock that caused so much widespread damage. And unfortunately, because we all know sound travels slower than light, people were seeing the meteoroid at Chelyabinsk out of their windows. So they went to their windows because they could see this thing burning up in the sky. So they're all standing in front of their windows looking at it. And then seconds later, the sound blast hits them, shatters the glass. And that's actually what most of the injuries were. They were glass injuries for about, I think, over 1,000 people. But anyway, enough of that. So anyway, you can take a look at that if you are interested, and keep an eye on this page for other close approaches. You can also change some settings in there as well. So that's quite cool to look at. So there we have it. There we have proof that we've captured it this evening. So thank you very much, Babak, for sharing that. Let's just hop back and see what else Slooh members have been looking at this week, because it has been, I would say, quite an eventful week. Carol from South Africa, thank you so much for sharing this one. I didn't want to share it myself, but when we were operating the Slooh solar telescopes, that's the Canary 5 solar telescope, very special telescope. You shouldn't point a normal telescope towards the sun, not unless you've got proper filters on it. And this one just looks at H alpha. So this is the hydrogen alpha line, the wavelength of light. So we land up seeing the chromosphere, not the photosphere. So the photosphere, if you think about that, is the kind of thing that we see visually in the sky. Or if you put a pair of eclipse glasses on, that's what you're seeing. You're seeing the photosphere. And that's where sunspots are. Right? That's why you can see sunspots so well in a white light filtered telescope or eclipse glasses. But what we're looking at in the special solar telescope is hydrogen alpha light. And what we're then seeing is we're seeing the chromosphere, and that's when we start to see loads more detail. And today we tuned it, so we increased the exposure level and tuned the filters so that we could see these massive prominences coming off the limb of the sun rather than the surface detail. So let's say surface is the chromosphere, but in other words, the exposure is long, so that all gets wiped out, but we do see these fabulous looking prominences, which are, if you remember, sun's magnetic field lines breaking through the chromosphere, actually breaking through. They're actually what are rooted in sunspots. So they're coming from the photosphere and bursting through the chromosphere and usually looping back. So they're usually bipolar, like a bar magnet is. And what happens is they channel all of the hot plasma up through those magnetic lines. And do have a look in discussion boards, because I think it was Cameron did that fabulous animation of them over a day. But just to give you a sense of scale on this, you see this gap between the prominence and the sun that I'm pointing at. The Earth would fit in there 4 times. I mean, these things are just gargantuan. I find it very difficult to comprehend these things, some of the solar features. So anyway, they've been looking great. And all of that lot means that those are emanating from what's called an active region. Now, we know that the solar telescope, the sun spins in this particular view from left to right. So we know that the active region that those prominences are coming from are going to swing into view later on this week as the sun spins on its axis. So that's going to be pretty good. And look at this. So this is from Paul B. Hi, Paul B. I haven't seen you post anything before. Thank you very much for doing this. I think this was the last mission from last night from Chile. So it's the Chile 1 telescope. And that's the reason why it's looking a bit strangely coloured, because it was under twilight skies. But here we can see, in fact, look at this. When I set this mission up, I even said it is at low altitude, at the end of the night to warn us. But look at that. This comet certainly has not been disappointing. So Paul B, thank you very much for sharing that. Let's hop back, see a little bit more. A couple of great Running Man nebulas there. But they're not our quarry tonight. Where are the comet shots we've got here? I don't know what Alessandro is sharing. That's Crab Nebula again. Oh, look at that one. So here we go. This is Canary 1. So this is the half-meter telescope last night. And look at that. This comet really isn't disappointing, is it? And don't forget, it's not too late to spot this comet with your own eyes. Hopefully you've been, I'm just taking a look to see if I've shared these in the discussion boards. I don't think I have. But if you've been keeping an eye on our Twitter feed, then you'll know that we've been sharing sky charts, finder charts for you for every morning. And the last one that we published is for tomorrow morning. So if you are able to get up a couple of hours before dawn, that's best, couple of hours before sunrise, really, this finder chart will tell you where to look for Comet 21P Giacobini-Zinner. And it is well worth taking a peek, because it is well worth looking at and quite easy to find tonight and tomorrow, because it's very close to a star cluster, an open star cluster. So that probably takes us on to our next little subject, actually. Because it is it's the special missions. In fact, no, what we haven't done yet is, we're going to let's do this. You know me. Run with me, folks. Run with me. We're going to take a look ahead at the special comet missions that we've set up tonight. All right. And then we're going to go back, because I've got something special to tell you about Comet 21P. And its third tail. Tail of the comet. Anyway, so what have we got here? So special missions. There is a post here in the discussion boards that you can look up, and it lists down all of the special missions that we've set up. First of all, for NearEarth Asteroid 2018 RC, they have now finished because it was only visible from the Canary Islands in the first kind of half hour, something like that, of the night. But here we go. These are the ones that you want to pay attention to. So Comet 21P Giacobini-Zinner, And thanks very much, by the way. It was Dell who told me I was pronouncing Giacobini. I was pronouncing it Giacobini, but now I can't say it any other way, Giacobini. And Dell told me it was Giacobini-Zinner. So thank you very much for that. But look at this important bit that's added on to this. So Comet 21P, Giacobini-Zinner, and M37 on Sunday and Monday. So what is M37? Well, if you've been into astronomy for any period of time, you'll know that this particular set of kind of code stuff is quite easy. It's the Messier catalogue. So this Charles Messier, comet hunter, 1700s, created a catalogue so that he wouldn't confuse star clusters, galaxies, nebulae with what he was looking for, which was comets. And he numbered them. And this particular one is called M37, so Messier 37, and that is an open star cluster. So it's a loose grouping of stars. Usually they are associated by their birth. So quite a few of them are born at the same time, probably in quite a compact, dense region of dust and gas. And sometimes they can be very large stars. So the Seven Sisters are probably one of the most recognizable open star clusters. But because the clouds of gas that these things are born in are so vast, the stars that they form can be very big. And if you remember, large stars, they live fast and die young. They burn out their nuclear fuel so quickly. So they can sometimes last only millions of years rather than billions of years. I mean, our sun isn't even middle-aged yet, and it's 4.5 billion years old. So some of these stars do. So anyway, M37 is this open star cluster, and this is why Comet 21P is so easy to see in the night sky through a pair of binoculars if you go out tonight or tomorrow night, because either night actually will be a good pointer. But anyway, look, you can see here that we've got these special missions set up. Sunday night, we've got Canary 1. We haven't done Canary 1 every single mission. We've only done every 30 minutes. On Canary 2, we've done them every 15 minutes tonight. But then on Canary 3, because it's the least used telescope, we've actually done these back to back. So all of the missions from 0115 UTC, that's in a couple of hours' time, 3 hours' time, and running all the way through virtually until dawn. And the way we framed it up includes the comet and the open star cluster. Now, tomorrow night, Canary 3 is also set up in the same way. So it still shows up in the same, both objects show up in the same frame. But you can see here that on Monday night for Canary 1 and Canary 2, we've actually set up what we call mosaics, and they're 2-panel mosaics. And what that means is that we've joined 2 missions together, one taking an image of the comet, one taking an image of Messier 37, the star cluster, and then you'll be able to join those 2 images together to make a larger image, including both of those missions. So anyway, that's what we've got coming up tonight. Babik looks like he's sharing another image. Actually, that was, okay, this is of 2018 RC last night. So you can see it was moving pretty darn fast last night. And Carol was just saying that she was watching missions last night as well. So they were quite cool. So anyway, there it is. But I think I should show you something a little bit easier. Yeah, actually, so this shows what the mosaic is going to be like. In fact, let's just open this up in a new tab so you can see a bit better. So here we can see, this is tomorrow night, and we can see here the grey boxes, all right, are the field of view of the Canary 1 and Canary 2 telescopes, give or take. And what we've done is you can see that they overlap here. So we've set up some missions on this box saying that's M37, and we've set up some missions in this lower box, A2, which shows Comet 21P Giacobini-Zinner down in the bottom left. So you'll then be able to join those up so that you can get an image tomorrow night as well. But they will be appearing in Canary 3, both at the same time. So how do we know that? Well, let's just take a little look here a second, because we're going to go over to our media show that. Right, so this is Stellarium, our software of choice. So what we want to do is see how we know that in the Canary 3 field of view, and don't forget, the Canary 3 Deep Sky Telescope has one of the largest fields of view of any of Slooh's telescopes. In fact, it's second only really to the Canary 2 ultra-wide field. We've got some tricks coming out that we're hoping to get an even wider field of view as well. But here we go. So we're looking at this now, and we can see down here from the status bar, it's set to roughly when I just started this up. So we're going to stop the clock there because we're interested in a particular date and time, and we know, because we've been doing lots of scheduling, that the Comet 21P rises after midnight and actually is well placed kind of from 3 or 4 on, but actually we've scheduled missions before then, so let's just get that to a round number, otherwise my OCD starts making me shake. So anyway, there we go, we set the date and time. I already know that this is Slough Canary Islands because we've set the observer condition down there. Then we want to do our search on it, so 21p / Giacobini-Zinner, there we go. Oh, and he makes a typo, so that won't work. Zinner, there we go. So there it's showing us where the comet is. So let's zoom in on it. And the best way of doing that for our purposes, we really want to see the telescope fields of view. So don't forget, you can download this software free, and in the discussion boards, we've also added in there all of the configuration files that will set it up just like you're seeing it here. So if we come up here to this little thing, and we can start seeing fields of view. So it's automatically zoomed in on the comet, and at the moment, as default, this is showing the field of view. So the big red square, that's the field of view of the Canary 1 telescope. But if you take all of those configuration files from discussion boards, you can flick these on: Canary 2 wide field, Canary 2 ultra wide field, Canary 3. Don't forget, we also need to change the telescope as well. So it's the telescope and the camera before it gives us the true field of view. So there we can see 21p Giacobini-Zinner. And hey, look down here. It says salt and pepper cluster. Now, some people call this salt and pepper cluster. Others call it the gold dust cluster. And here you can see I just dragged it across here. And there you can see that the comet's at the top. The M37 open star cluster is down here to the left. So they both fit within the same field of view. And if we change the date now to tomorrow night, we can see that the comet has moved on. So we've now got the cluster above it and the comet below it. And this is why it won't fit quite in the Canary 1. Let's just hop back and do that in the Canary 1 telescope. Change the camera as well. And you can see here, it doesn't quite fit. In fact, that's the wrong date now. So let's go back on that. Oh, there you go. Oh, and now I've lost it all. There it is. Yeah, so you can see it's not going to fit within the same field of view. So because you can see Giacobini up there and the cluster down there. So that's why we're using Canary 3 telescopes. So that's how you can kind of set up your missions and visualize your missions. Because frankly, unless we were able to do this, let's just go back to the Canary 3. We are talking about practical astronomy after all. It would do us no good to set up a mission to M37, because if we set up a mission to M37, that's where it would be. And you can see that the comet's outside of the field of view. If we set up a mission to the comet, then that's where it's going to be. So the cluster won't be in our images. So this is how I visualize the missions before I set it up. So the way I visualized this was, we know that the comet's tail is going off to the right because it's going away from the sun. So that's heading west. And there we can see the cluster. The cluster's fine. So we want to get as much of the right-hand side of this comet as we can. So what I did when I set these up is I kind of positioned the field of view so that the cluster was fully visible down in the left-hand corner, which showed us as much of the comet as possible to get as much of its tail as possible. Then all I did was select the center point of this field of view or an object near it. And you can see here it's given me the coordinates for me to set up my own coordinate mission. And that's how I've done it. And that's also how I did it tomorrow night. So tomorrow night, I did the same kind of thing, but thankfully both of them are on the same side now. So there's the cluster, and we can still get the comet in with the tail shooting off to the right-hand side. So that is just a little how-to, how I set those missions up. So let's just get back to the right screen. Here we go. Right, so you've got all of that lot to look forward to tonight. And the first of those missions starts in roughly 3 hours' time. All right, so, and they run all night long. And we can do a time lapse, of course. But anyway, so there's that one. Let's just hop back. So we've done that. We've done that. Right, so we said that we're going to look back at some of the great comets that we've seen on Slough over the years. And in this thread, I shared some of my favorite comet images of all time. And some of these are Comet Lovejoy, others, some are others. I would highly recommend you look at this post in discussion boards, because the screen share and the broadcast will kind of, distort some of that, and you won't see quite as much detail. But there are some beautiful fans of detail coming off the side, off through the tail. And this is the comet that we saw the tail break away several times. And this one we're going to come back to. I wish I'd labelled these. I should have labelled these, shouldn't I? I think a lot of these are Lovejoy, and I think one is one of the Pan stars. So there's a nice one. There's Q2 Lovejoy from 2015, when it was putting on its spectacular show. And this was using the Chile telescope. And I just thought Jean-Paul put this image together. And what I loved about it was that he put the moon into this kind of montage just to show us the scale. So that is actually an image that he took with the Chile telescope. And he's just included it in this montage because the rectangles are 3 separate images that he took. It's a mosaic. It's what we were talking about before, so that we could see all of the tail. So he's joined the images up. There's a funny little white line here. That's actually a satellite that's gone through the image while it was being taken. But I just thought that was really cool, just to kind of put this in perspective, really, in the field of view of the camera. And this is my favorite. I mean, this is Q2 Lovejoy as well. And this is my favorite Slough comet image of all time. From David Malik, you know that I'm a great fan of David. You'll see him post his wonderful image processing in the discussion boards. And this just blew my socks off. I mean, just look at the level of detail. I mean, it's probably worthwhile, actually, if we open this one up in a separate panel so we can take a slightly closer look. But look here, you can even see there's a galaxy here that's also showing up. Obviously all the stars that we see are in our galaxy, but that galaxy is in one well beyond. But look at the coma. So we've got the coma here. We've got dust and iron tails coming off here. And this tail just disconnected several times. And that can happen when the solar wind is particularly strong. And it literally just blows the tail so hard that it breaks off. And don't forget, this is just a trail of dust and gas. The ion tail is the ionized gas, which is being ionized by the particles, the high energy particles in the solar wind. And the dust is also being blown away by radiation pressure. But you can see the coma here. And don't forget, You know, the actual object, the actual comet nucleus is a tiny little thing in comparison to this image, right at the heart of that really bright comet. And that's exactly what we're seeing in 21P as well. So Lovejoy was one of my favorites. There's another one of Lovejoy. It certainly was, you know, one of the best. Look at that beautiful comet. I mean, it's just such a classic. Not sure what that one is. I really should have labeled these, shouldn't I? I'm sorry. The original names were on there. So this is Comet 96P. So this is another periodic comet. So don't forget the last one. If it's got a name like C2015 14Q2, that's a non-periodic comet. It may come back, but when it comes back, it'll be longer than 200 years away. But a periodic comet is one that comes back to our neck of the woods within 200 years. And this is also, it's 96P Mascholtz 1. Now, Mascholtz is actually a lovely chap who's a Slooh member, and he's discovered several comets. And whenever they're due to come back, we always exchange emails, and we make sure that we capture it together, which is always fun. But that's that one. What have we got there? Oh, Hergenrother was another good one. And we interviewed Carl Hergenrother on a show around that time. So that was quite cool. And we were seeing both of these comets at the same time, which was really quite cool as well. Oh, and there's another one. So we're looking at time lapses later. Now look at that. When you just look at the still of this image, how much of the tail do you see? Well, you do see it, but frankly, it's a lot easier to see the fainter detail in the animation. What's cool about this one is, as well, you can see this little galaxy up here as well. So that's quite nice. I love that image. And we've got another one, and oh, that looks like Lovejoy again. So anyway, if you've got any of your favorite comet images from the last 14 years of slewing, then please share them on this or another post. Let's just take a quick look, make sure that we haven't got any questions here that I need to pick up on here. Stephen, thank you so much for all of the information that you've been giving us about all of these objects and stuff like that. Now, we did see 2018 RC get very close visually to Comet 65P Gun. Now, I haven't had a chance to take a closer look at those images to see if it was possible to see 65P Gun, which is quite faint, very faint at the moment. So I haven't done a check on that. So yeah, David's just saying that we've got loads to look at the moment in the telescopes. David H just checked it with Stellarium. Yeah, thank you very much for that info. Yeah, it's Horizon. Yeah, people were talking about, how do you get the coordinates for, this fast-moving object? Because I had noticed actually that a few members had set up missions to NearEarth Asteroid 2018 RC, but their coordinates, I don't know where they were getting their coordinates from, but they were certainly quite a long way off. There were even a couple tonight actually that are scheduled. So if you do want to do that, then do take a quick look at that little video, all the previous live casts that I've set up. Here, and David's just set up this tiny little Where's Wollaton as well. Wollaton, isn't it? Yeah, Wollaton. We were saying where's Wally, or whatever that thing is that kids do in their book. And there is that tiny little comet. So you can see that, that's actually what 21P was looking like, before it got closer and closer to the sun. So anyway, there's a good little roundup there. But I did want to say, actually, I was going to go back, wasn't I, to one of these images here, because we see something quite strange in this particular image. We can see we've got the normal dust and gas tail coming off the right-hand side of this comet. But what the heck is this thing going off to the left? Well, we know, we've just said, that comet tails always point away from the sun, because it's not so much the trail of debris left behind by the comet. It's the solar wind is blowing it. As soon as it leaves the comet, the solar wind, the solar radiation pressure is blowing all of that gas and dust away from the sun. So that's why actually in Slooh comet missions, you so often see, if it's an evening comet, then you'll see it going, the tail going from left to right. And then if it's a morning comet, you'll see it the other way around. But what then? How on earth is this explained? This tail going off in totally the opposite direction? Well, this is called an AntiTail. And I don't know if you've heard about AntiTails before, but this was actually the first comet, I think, that I discovered them on. I didn't discover them, but I discovered personally. And an AntiTail is made up of larger dust particles. And those larger dust particles, they're not affected by the sun's radiation pressure anywhere near as much as the smaller particles and the gases. So imagine in this comet here, we've got smaller particles and the gases being taken off in one direction away from the sun by that radiation pressure. But what is in here are the larger particles, which aren't blown so readily by the sun's radiation pressure. So they remain more or less in the comet's orbital plane. So just imagine if it's a periodic comet, it's going to be kind of an elliptical orbit. Just think about joining that up into a kind of disk, and that is the comet's orbital plane. So those larger dust particles remain in that comet's orbital plane. And that over time forms a disk of material along the comet's orbit. Now, there's a very special time when you can see a comet's AntiTail. And it's when the Earth passes through the comet's orbital plane. Imagine what we're looking at here. Imagine that this thing is not a line, as we're seeing, a wedge. It's a disk. But we happen to be seeing this disk from edge on because we're seeing it when this Earth was passing through the comet's orbital plane. When we're not passing, we're either above it or below that disk. And then it's not dense enough to be able to see it. So you can sometimes have a very short period of time, sometimes a single night, when it's possible to see a comet's AntiTail. And it's when Earth passes through the comet's orbital plane. And that's when we're seeing that disk side on, edge on. And it can look as though a tail is pointing towards the sun, the AntiTail. And I just think that I was one of those lovely little bits of astronomical knowledge, which when I first found out about it, just kind of reminded me why I find astronomy so exciting. And yeah, it's just, I don't know, the older I get, and I know I've spoken to other members about this, the older I get, the greater my thirst for knowledge becomes. And I always think that life is around the wrong way. I think as, when you leave school, you should leave school, everyone should leave school either 16 or 18. They should go off, do menial jobs for at least 10 years, probably 20, maybe even longer. And then when you are ready, when you thirst to gather up knowledge, then you go to college or university. And I tell you, all of the students would make the most of it if they were all my age. I know they would. I know I would love to go back to university now. My quest for knowledge. So anyway, when do you know? That was a bit of a meander, wasn't it? But when do you know when Earth is passing through a comet's orbital plane? Well, I've got another little website here to share with you. And it's called Calsky. Now, I use calsky.com quite a lot. I've set up my own email alerts using this particular website. So they send me through a daily alert. And look here, we can see here, we've got, we can see, I've actually set this page up already, so it's on Comet 21P, so that's what it's giving us. And we see there the orbital diagram. Well, okay, well, I guess we could make out when Earth is going to pass through the comet's orbital plane, but not that easy. But keep scrolling down the page, and don't forget you can do this for any comet. There's a useful little thing actually that you can look at. This is the light curve. Now, what we can see here is just dates on the bottom and magnitude, and this is visual magnitude on the left-hand side. And what you can see is you can see some curves there. So those are the estimates. So that's our best guess based on what we know of this comet. But then you can see all of these little purple spots, and those are actual brightness measurements. So people have performed what's called photometry on the images that they've captured to measure the comet's brightness. And that gives them the magnitude, and it can then be plotted on this light curve to see how bright it's getting. So we can see that this has kind of been bumbling along kind of roughly where we're expecting it to. It hasn't done so much what we've seen on some other comets over the last few months, which is a cometary outburst where suddenly the brightness hops way up. In fact, we can see one here, can't we? There is quite a brightening here, well off the line, so around June time. And these are these cometary outbursts that we looked at last week. But if we scroll down even further, this is telling us about all of the phenomena for this particular comet. And look up here, Thursday, 5th of April, 2018, it says Comet 21P Earth, 21P, Earth crosses comet orbital plane. It tells us greatest elongation, that's when it's furthest away from the sun, maximum declination north, brightness, and then if we scroll down, we can obviously see here, this is what we're really interested in here over the next couple of days. So at 7 point, when you see this, 7.7, that means 7.7 hours there. So, excuse me, we know this is happening tonight. Comet 21P is at perihelion, which is when it's closest to Earth. But then by a remarkable coincidence, and this doesn't happen very often actually, it just happens to be because of this particular comet's orbit and its relationship to Earth during that orbit, that perihelion and it being closest to Earth are within 7 or 8 hours of each other. Because here we can see later on tomorrow, we've got Comet 21P is closest to Earth. So both of these things happening at the same time is why this is one of the best apparitions of Comet 21P that we've had for donkey's years. Back in 2012, the apparition now, an apparition is just its viewing season when it comes into view, when it appears to us. The 2012, it was hopeless. When it reached perihelion, it wasn't really visible from Earth very well. So what we're seeing here is at perihelion, it's at its closest to Sun. So it's being pummeled by that solar radiation and making it very active and spew off lots of material. But it's also closest to Earth. So it appears bigger in the sky for us and brighter as well. So those two things put together mean this is a really good apparition. But what we're talking about is AntiTails. So scroll down here, we've got 15th of September, descending node passage. We've got Monday the 1st of October, Comet 21P descending equator passage. But Tuesday the 9th of October is the one that we're interested in. Comet 21P, Earth crosses comet's orbital plane. So what we need to do is we need to check, is the comet still going to be visible on the 9th of October? And if it is, we're going to see whether or not we can spot its anti-tail. Because I tell you, it is a really cool thing to see if you haven't seen one before. So anyway, that's so we got all of that to look forward to. So that is Calsky. So I'd highly recommend you take a trip over there and set up your own set up your own email alerts from them. They really are great. They'll give you a little calendar of everything that's visible in the sky and everything like that. So anyway, let's just take a look where we are. Actually, I've got this open in another window. So we have looked back at some of the great comets. We are looking ahead to we've looked ahead at some of the special missions that are starting tonight. We're not going to do the comet coordinate mission. You can look on Twitter for that. Creating a comet time-lapse. Shall we do that? We got 5 minutes. We're only going to go through this quickly. So let me just set some stuff up on my screen. Dun, 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 dun. So, here we go. Look at that. Loads of comet images. These are Canary 3 last night. And it always opens up on the wrong screen, so it doesn't share with you. That was the first image of the night. Excuse me. So it's looking pretty washed out there. But we're going to do something about that. In fact, I'm just going to delete that first image there. We don't want that. In fact, yeah, that'll do. So actually, no, we'll use this test. We'll use this test group of images. So there they all are. Now we could, if you remember, we could just use our animation shop software, which is free to download in the discussion boards. And we could animate and turn them into an animated GIF. And you can see here that the stars are not moving. I'm flicking through each image now. Oh, look at that. Great satellite there whizzing through our field of view. But you can see the stars are not moving very much because I set these missions up with the same star field, so the same coordinates, so the comet would move through it. So, but if you're looking at that, by the way, the satellite streak and wondering why it goes bright, dark, it's because that particular satellite, it's probably a communications satellite, is spinning. Excuse me, take a drink. And a lot of satellites spin because it makes them more stable in orbit. So you could just get this lot straight in, but you can see there's a little bit of movement in the background stars, which can be a little bit distracting. Here we can see, look at that. We're over twilight now. So when we're out of that, or actually it was low, it wasn't twilight, it was when the comet was really low. So now it's getting out of that haze and we've lost a lot of that green background color that we were getting. And here we go, we can see this. But I think automatically now, you can start to see more detail in the tail, in a moving image, in an animation of it, rather than just any single image. So as I say, we could pop those directly into let me just find some other software that I've got, into our animation software. But we're going to do a little bit of work on it instead, I think, on this one. So we're going to use Maxim because it's just the quickest thing for me to show you this. And by the way, these are the PNGs I'm working on tonight. We are not working with that FITS data. You know, the FITS data, the scientific stuff that astronomer members get from their missions, where they can do their own image processing and stuff. You can still do all of this stuff on these, the PNG images. So there we are. We've opened them all up. I didn't actually count, actually. How many of them are there? Were you counting? Was anybody counting? 58. So we've got 58 images here. Now, what we can see here is we've got that green tinge, and we saw that kind of slight misalignment of the stars from one to another. So I'm just going to go up here. I'm going to show you something in Maxim, which is this software. It's very expensive software, unfortunately, a few $100s. I'm going to go to the batch process window because I'm not sure if you've all seen this. So what we're going to do here is I'm going to press the record button. And I think the first thing we'll do is we'll get rid of this color because the color's not adding very much to it and it's detracting from the low missions. We're going to say convert to mono. And you can see here, Maxim has done it on that particular image, but this batch processor has also recorded that step. I'm also going to apply a little curve function on that to brighten it up, and it's recorded that as well. Now I'm going to stop recording. I'm actually going to undo it on that particular image. And now we've got it. But now what we can do is we can say, select all of the images I've got open at the moment, and please just do that same thing on all of my other images. So it's going through each and every one of them, and it's converting each of them to grayscale, monochrome, and applying that same curves on it. That was because the one I'd already done, which is why I couldn't have done that. So it's going through, and it's going through 58 of these things, which actually gives me the chance to take a little sip of water. It's going to be the last thing we do tonight, and it will be very quick. So we're going to be another 5 minutes or something like that. We will just check on questions if you do have any. So I know this is watching, but these are really large images. Even these PNG images are quite large. But just look at how much work this is saving us. Now, you could refine all of these steps. You could add in other steps to this batch process as well. And I actually do this on some of our planetary images at the observatory every day in Chile to reduce the size of those. So this is an automatic process that runs. So here we are. Okay, that's them all done. So, wow, look at this one over here, look. You can see how far back, you can actually see the tail coming back here where I'm pointing. Isn't that cool? Now, we could, of course, do all sorts of stuff with this at the moment. We could combine some of these images over a shorter period of time so that we can see even more detail in the tail. But we're just going to align these at the moment. So I'm just going to add all of these to the alignment process. It's showing me a little preview of it there. We'll try a star match. It might not work on star match, but we'll try it. This does work better. The automatic alignment does work better on the fits, tends to. But we'll see whether or not it manages to do this. It might be that we have to do autocorrelation, which is a good kind of substitute for that. No, couldn't do that. So let's try the autocorrelation. Autocorrelation is one that often works well with images where there's a large amount of bright nebulosity. That hasn't really hasn't aligned them as well as I had hoped. So actually, I'm going to cancel that, and we're not going to spend time on that because I could set that up in another alignment routine, and we could get that alignment absolutely perfect. But after we've done that alignment process, and don't forget, we've seen how to do that in other programs as well. You can do it in any layer-based image processing software. But let's, for the sake of argument, say that we have aligned these. We know that they weren't badly aligned anyway. And the nice thing that we can do in Maxim is we've got this animation view. So it's asking me which images do you want to look at in this animation. Here we go. Here's a preview. Let's get it a bit bigger. Not quite that big, Mr. Cox. Thank you very much. So let's get it in there. Let's fill the screen up with it. And you can't see this little box that we want to see. So what should we do? Shall we set the animation at 0.2 seconds, 0.5? 0.5 might be a bit slow. You can step through it, image by image, or we could play it. And there it goes. So we can see that's a bit jumpy. So let's go down to 0.2 seconds. That's a bit smoother. We could even go down to 0.1 on this, I think. And we are still getting those stars moving a little bit in the background, but you can see immediately that as soon as you have a moving image, our eyes get to see so much more of the tail. And this is just with the PNGs. You know, there's been no other processing on these from what you've seen. And the Canary 3 images, don't forget, are quite noisy at the moment because the CCD is not reaching its proper cooling temperature. But the only reason why I wanted to do this kind of quick and dirty tonight is to, one, show you that you can work with the PNG images, but secondly, on your Comet images, it's not just about the fun of creating a time-lapse animation to see this object moving over a period of time, but it's actually that you land up seeing far more detail in the animation than you do in any single frame. This also, as well, is a perfect illustration of what we were talking about earlier, where we can see that the comet's tail is going off to the right, yet the comet's moving from top to bottom. So the tail is not trailing behind the comet. The tail is being blown by the sun's radiation pressure, the solar wind blasting off from the sun. So that's a great illustration of that, isn't it? So anyway, okay, we've done that. Thank you very much. Close that down, close that down. No, we don't want to save that a lot. I'll leave that up to you lot if you want to do that. Let me just get back to here and we will take a quick look at, see if you lot have kept me company tonight. Just going to open up the right window. Kept me company. Let's see if there are any questions. Don't think there were when we looked before. All right, Cameron may have done. So, hey, Cameron. Nice to see you again, Cameron. Spectacular. Is that now? Oh, that might have been now. Is there one down the bottom anywhere? Oh, right, yeah. Cameron spotted on that Calsky website 3D anaglyph, which means if you have got those kind of red and green 3D sunglasses, it gives you this three-dimensional view of the orbit. So this is the thing on Calsky that we were looking at, and you can see here, if I just zoom in a bit on it, you can see there it's kind of got the red and green offset. So that's really cool to do that. What I have noticed, actually, I noticed this today when I was using the site, and in fact the colored 2D projection, this is not working for me, so I don't know if it's working for anyone else, but switching between the two different versions. But anyway, Cameron, I'm glad that that's actually going to be useful for you. Did you say your student's going to look at that? Where was it? Where's it gone? There it is. Yeah, so your students are going to love that. Well, great. I hope they do. Was Hale Bops, Danielle M asking a question, was Hale Bops, and hi Danielle, I haven't seen you before in the discussion boards, but I see you've been a Slough crew member since 2017, so welcome, belated welcome. Was Hale Bops extra tail and anti-tail? I don't believe so, not when we were seeing that in its full glory. Let's just do a very quick little search on this and we'll get the classic images. Let's try and get one with the ground in play. So hopefully you can see this. It's actually an astro photo of the day. So these are the two tails. So we've got a dust tail in this one and we've got an ion tail. So the ion tail is that excited gas, those molecules and atoms of gas which have had electrons stripped from them by the sun's radiation pressure. So we know that this is probably a dawn image actually with this one, so that we know that that is pointing away. So the ion tail points away directly from the sun at all times. People can, any viewers, if I'm wrong on that, then put me right. But I believe the ion tail is the one that always points directly away from the sun, because it's the lightest particles, in other words. And then the dust tail, the whitish one that we're seeing here, is because they're larger particles, they're not affected by the sun's radiation pressure as much as the ionized gas particles are. So that's kind of a mismatch of comet's direction and the sun's direction. So it's not blowing them directly away, but it's still blowing them quite a long way away. So we're certainly not seeing, that's not an anti-tail. Neither of those two are anti-tails. So there really are three types of tails that we get for comets. We have the ion tail, which is that excited gas one. We have the dust tail, and we then have this very rare anti-tail. And as I say, you only see that over a period of a couple of nights, usually. I think I'm right in saying that. I'm just going to do a very quick search, actually, to see if there are any cool images of an AntiTails. Yeah, here's one. So this is a really good example here. So which one is this? This is Comet Lulin, right? So this is one that we did see actually at Slough. So this is a great example. So here we can see gas and dust tails here, but here we can see so just imagine if we were above the comet from this view, we'd be looking down on a disk of material. That disk of material would be so thin and so sparse that we wouldn't actually see it. But just as Earth is crossing through the comet's orbital plane, where that material is, where all of those larger dust particles have accumulated, we see it edge on, and that's when we can see it densely. So it's just as Earth is passing through it. So it's a little bit like the Milky Way, in other words. You know, when we're seeing it edge on. If we were above it, it would look a lot thinner and nowhere near as bright. So anyway, I reckon that just about rounds things up for tonight. Thank you very much for joining me. Thank you very much for any of the, in fact, I better do a refresh on that just in case I've missed any. So join me again next week. Cameron NASA states an object is 50 meters wide. Is the object a roughly spherical potato shape? That's always assumed, actually, Cameron. So when the size estimates are done from its apparent brightness and its orbital data, so right at the beginning of the show, we were talking about how do we estimate the size of an asteroid. Well, the only two things that we normally know about it are its orbit. Its orbit, we can tell how far away it is, how far away from Earth it is, and we can also measure its apparent brightness. We take that standard albedo. It's an assumption of how much light reflects off the surface of that asteroid. And then we calculate, okay, if it was average, it's going to be 30 meters wide, something like that. But the wide is spherical. But we know that so many of these objects, the more of these objects actually come into view of our radio telescopes, so we can actually build 3D models of their actual shape. We know that they are often two-lobed, two joined together. Comets are like this as well. We saw that in the Rosetta mission. So a lot of these objects are very, very weird shapes. But there is another way where we can start determining that. And we can do that by having creating detailed light curves for objects. Because if you can imagine, if an object was long and thin, when it was side on to us, it would be brighter. But then as it rotates and we see its end, it would dim quite a lot. Now, if we take sufficient measurements of its brightness over a period of time and measure when that brightness changes, we can then actually start inferring the actual shape of the asteroid as well. So that helps us pin down that size estimate even more. There is another way actually that we can tell the exact shape of an asteroid even without radio telescopes, and we do that by what's called occultation timing. So this is when an asteroid passes in front of a star. Now, this is a little bit like a solar eclipse. It's only visible from one place on Earth at any one time, but it's actually from one region. So what you tend to get is loads of amateur astronomers who are into occultations and the timing of those, is they spread themselves out on a path and they all time very accurately. They have these really precise GPS clocks, and they time precisely when the asteroid for them occults the star and when it reappears as well. You put all of those together over an area, and if you have enough people doing that over an area, you're basically tracing an outline, a silhouette of the asteroid's shadow from that star. That's really what you're doing. And you can get very, very accurate, very precise shape and size estimates of asteroids by using that occultation technique. So great question there, Cameron. And thank you very much, by the way, for being so active in the discussion boards as well. It's always fun watching looking at your posts and seeing all the other stuff that you're getting up to. Anyway, I hope your students enjoyed 2018 and Calsky and all of those orbit diagrams and stuff like that. That really is it then for tonight. Oh, look at that. We're just going to leave that with the Helix Nebula shared by Michel P. Thank you very much, Michel P. Canary 3. That's looking quite nice, isn't it? That planetary nebula. I won't go into that. Anyway, listen, I will see you during the week in the discussion boards. See you next weekend. Don't forget, we've got in 10 days, 12 days time now, we've got the September equinox show coming out. So we're going to be doing lots about solar science during the day with the solar telescope on that. And then we're going to be seeing sunset live from the west coast of the USA to celebrate equinox. So that's going to be quite good fun. Anyway, thank you very much, everyone, for joining me tonight. It's Paul Cox. It's been another episode of Practical Astronomy, this little special with Comet 21P, Giacobini-Zinner, and that near-Earth asteroid 2018 RC. By the way, 21P is going to carry on looking just as good. And don't forget, with a close approach to Earth and a close approach to the Sun, gravity of both of those bodies is pulling hard at that poor little comet. So who knows? It might disturb some of its structure, which exposes all those volatile ices, which means we might see a terrific cometary outburst. Anyway, let's keep our eyes on that every single night. Good night from me. Bye, Slough.